All right, folks, here's the big piece of meat, the main skill that you need to learn for this week of Chem 20. So we're going to be talking about net ionic equations. So I've written out an equation here. This is a regular chemical reaction equation. We've already balanced it. It's the one from the previous video. Lead 2 nitrate, I should say, combining with potassium iodide to make lead iodide, lead 2 iodide, and some potassium nitrate. So what a net ionic equation actually tells us is what's going on in the reaction. It's as simple as that. So one of the things, since we're talking about an ionic equation, we care about ions. Now, yes, this is an ionic compound, so is that, so is that, so is that. But here's what we're going to do. What we need to do to complete a net ionic equation is, first, we're going to dissociate every ionic compound that is soluble. So let's do that. So I'm going to write all of the things that are soluble on, where they're supposed to be, but I'm going to write them down in the correct amounts with their charges and their states, all of the little things that we are trying to train you to do. So I look on the left side and I've got lead nitrate, lead 2 nitrate. So I know that this is made out of Pb2 plus aqueous. And I also know that it contains 2NO3 aqueous. We've got 2K plus aqueous. And I'm going to have to scoot this arrow over a little bit. And we have 2 iodide minus aqueous. So there are the reactants all dissociated, busted apart into the ions that make them up. Now, here I dissociate every compound that is soluble. So I look at my PbI2 solid, that is not going to get dissociated. It doesn't dissolve in water. So I just write it the way that it is. PbI2 solid. Now we have our potassium nitrate. That's going to make 2K plus aqueous and 2 nitrate ions, 2 NO3s, aqueous. So we've dissociated all of the ionic compounds that are soluble in water. Now we're going to do step 2, and it's very simple. Oh, I don't want to rotate. What's going on? You're going to cross out all of the arrow or all the ions that are identical on both sides of the arrow, and I just noticed that I did not put my minus charge on my nitrates on the reactant side. So we're crossing out all of every chemical species that is identical on both sides. The reason why we do this is because if you got nitrate ions on this side and nitrate ions on this side, did they undergo a chemical change? No. They're just there. They're sitting around. We call them, in fact, spectator ions. They're ions that didn't do a chemical reaction. They just kind of sat there. So let's hunt for some spectator ions. Obviously, we got two NO3s on both sides. So there's my two NO3s. There's my two NO3s. Goodbye to you. Then I have my two K pluses, and I've got my two K pluses. Goodbye to you. And now that we've crossed out all of our spectators, the third step is just rewrite whatever we got left. That's our net ionic equation. So I'll change back to, I'll do dark blue. So my net ionic equation, in other words, what is actually going on when we mix these solutions? The Pb2 plus ions from the lead nitrate are gonna hook up with the two iodide ions from the potassium iodide, and they're gonna form lead 2 iodide. This is why a lot of the time when you mix two ionic compounds together, you might not actually have anything cool happen. So, for example, the most important thing is if you make a solid or a gas, think about what happens in a chemical reaction when you make one of those. If you make a solid, the solid is going to fall down to the bottom of your beaker. Remember, that's called a precipitate. If it falls down as a solid to the bottom of the beaker, it's locked up. It can't do any chemical reactions in the water because it doesn't dissolve in water. Same logic applies for a chemical reaction that makes a gas. In a chemical reaction that makes a gas, the gas bubbles out and it just like leaves. Like if you mix vinegar and baking soda together, you get carbon dioxide gas, and that piece is out, it's gone. It's no longer in the solution, so it can't do chemical reactions. So a net ionic equation tells you what is really doing the work in the chemical reaction and what it's making. So the nitrate in here and the potassium ion, who cares? Like those guys just, they're spectating, they're watching this take place. A good example of if you mix two things together and no reaction happens would be something like this. Would be something like this reaction. So we have sodium nitrate, NaNO3. We have KCl, that's potassium chloride. And if I wrote this down on an exam and I was like, oh, predict the products, sodium chloride or potassium chloride and sodium nitrate mixed together, what does it make? And you, as someone who is, more than halfway through Chem 20, you'd be like, oh, Mr. Lorenz, I know what this makes. This is a double replacement reaction. And then you'd be smiling and thinking, nodding and thinking you're just crushing it. And if I gave this to you in a Science 10, yeah, I mean, you'd be right. Technically, it looks like it's a double replacement reaction. If we perform a net ionic on this guy, though, you're not going to see what you expect. Oops. K plus, aqueous. And they can get very long. I'm going to tweak this and shorten it in a sec. Actually, I'm just going to adjust these. That's my plus. That 3 is little. That minus is up top. The aqueous is little. Remember, folks, you can use in Google Docs. You can write, like I said, you can do these kinds of questions on paper. I have no problem with that as long as your writing is not complete 2-year-old like mine sometimes is. But if you want to, you can hold down the control key and then hit the comma, and in Google Docs that'll make this happen. And if you hold down control and hit the period key, it'll make that happen. So you can actually get superscript and subscript in your Google Docs, which is awesome. Like, it makes it doesn't save time. Once you get quick at it though, it's really not that bad. And I think it's pretty handy. So I'm just going to shrink this down so we have a little bit of space. And then we'll see what we have. Now, if you noticed, I did a little bit of something. I copy pasted. So the reason why I did that is because all of the things in this reaction are aqueous. So sodium, it's not doing anything. Nitrate, nothing. Potassium and chloride. None of the things in this reaction actually do anything. So we crossed out all the spectators, and yeah, we actually find out that in an aqueous phase, if you mix some sodium nitrate solution and some potassium chloride solution together, nothing really happens. All of these ions are perfectly fine just being ions. None of them do a chemical reaction. So let's take a look at another one here. Let's take a look at a single replacement, okay? So I'm just going to scroll down and let me just dream up a single replacement. Let's do, I don't know, Zn. Actually, let's do Zn3PO4 2. That would be zinc phosphate. Ooh, actually, let's check to see if that guy is even soluble. I have a feeling it's not. Ooh, it's not soluble. So you know what? Let's not use it. Let's use zinc sulfate. So ZnSO4, we don't need the brackets, and we for sure don't need the 2. There we go, because zinc is bringing a +2 charge to the party, and sulfate is bringing a -2 charge to the party, so ZnSO4. Let's say we drop let's fix that. Let's say we drop some, I don't know, let's say we drop some sodium into the mix. So sodium metal. So I've got a zinc sulfate solution. I'm dropping some sodium metal into the reaction, into the solution, to see what's going to happen. And our question is going to be, okay, is anything happening? So we're going to do a single replacement here. So that means we're going to have Zn solid. Where did that come from? Here. And we're also going to be making some good old sodium sulfate. Now remember, when you do this, what is the charge of a sodium ion? It's a +1. What is the charge of a sulfate ion? It's a -2, which means we need 2 sodiums for every sulfate. A lot of students, and you guys were pretty good at it, a lot of students who don't understand what's going on, they'll just go, oh, NaSO4, we got an Na from here, we got SO4 from here, we're good, great. That's not how it works, though. You have to make sure that your charges in an ionic compound are balanced. So there we go. And that is also a bracket AQ. Just to check, yeah, every sulfate is soluble except for these dudes down here. So yeah, we're in good shape. So now we're going to write our net ionic equation. And I'm just going to do it in pen because it's a little bit quicker. Pardon me. So we break up every ionic compound. Oh, actually, before we do that, we are going to have to make sure this bad boy is balanced. So we have one zinc, that's good. One sulfate, beautiful. We have 2 sodium, so we're going to have to throw a 2 out front there. Now we're good. So we have our ionic equation. We're going to break all of our stuff down into ions, which remember is called dissociation. So Zn, 2 plus aqueous. We have an SO4 with a 2 minus charge. That guy is aqueous. We have 2 sodiums. Those guys are solid, not aqueous. We're making Zn solid. We're making 2 sodium ions, which are aqueous. And we have an SO4, 2 minus aqueous. Boom. Beautiful. Now we can start crossing stuff out. Whenever you cross stuff out, remember it has to be exactly the same. So you are not going to cross out Zn2 plus and Zn. Are they the same? They're the same element. They're both Zn, but this guy is a Zn zinc ion with a +2 charge. This is a Zn atom with no charge. So you cannot cross them out. They're not spectator. The spectator ion in this case is our sulfate. So we are just going to knock the sulfate out, and now we rewrite the reaction with whatever's left. So we have Zn2 plus aqueous plus 2 sodium solid, forming Zn solid and 2 sodium ion aqueous. That's a net ionic equation. So some of you are going to think even harder with your brains, and that's awesome. I'm glad you're thinking with your brains. Some of you might be thinking, okay, so what does this actually mean? If you look at the NAs, they went from being Na solid to Na plus. So I'm going to write something underneath here. Bio 20 kids, you might remember this. Also, if you took Science 20, which I think some of you did. This guy, these 2 sodiums, they lost electrons. That's why their charge went up by 1. So how many electrons did they lose total? Well, each one lost 1. There's 2 of them. So that means that 2 electrons got lost. Where did those electrons go? Well, look at Mr. Zinc here. Zinc used to be a 2 plus. What happened to it? It became zinc neutral. Its charge went down by 2. Hey, wait a minute. The charge went down by 2. How did its charge go down by 2? It took the electrons from the sodium. And that is a phenomenon. So I'll say gained electrons, and it was reduced. So when something loses electrons, it is oxidized, and when it gains electrons, it is reduced. So this guy, sodium, is an electron giver-awayer. It's an electron donor in this case. And zinc 2 plus is an electron receiver or recipient. This is just a little bit of a head for when you guys talk about redox, oxidation reduction reactions, which you will see in Chem 30. So what's really going on is a transfer of electrons. Let's scroll up here and see if there's a transfer of electrons going on this bad boy. In this case, no transfer of electrons, just we have ion, ion coming together. None of the charges change. So let's do one more example. Let's do an acid. So let's do a very simple one. So we'll have HCl aqueous mixed with barium hydroxide. Now I have a feeling that barium hydroxide is not soluble. Hydroxides, most. All right, so this guy's going to be bracket S. Actually, that's not going to work. Let's say that it's going to be aqueous. And again, in certain conditions, you can get barium hydroxide solution. You got to heat it up quite a bit. But anyways, you're going to get H2O. Why? It's an acid giving an H and a base giving an OH. And we're also going to end up with BaCl2 because barium has a charge of +2. Chloride has a charge of -1. This guy for sure is aqueous. And we need to make sure it's balanced. There's 2 Cl here, so I need to throw a 2 here. There's 2 H's and 2 OH's. That makes 2 H2O's. So we've got our balanced chemical equation. Now I ionize or dissociate everything. So remember HCl, it's a strong acid. It's going to turn into 2H plus aqueous plus 2Cl minus aqueous. Then we've got our barium 2 plus aqueous. And we have our 2OH minus aqueous. And that is going to form 2H2O liquid. It's a molecular compound and it's neutral, so it's H2O liquid, it's not ions. And then we have our barium chloride, which is composed of barium 2 plus aqueous and 2 chloride ions, aqueous. Now we go through and we cross everything out that is identical on both sides. I'm seeing Mr. Barium is identical on both sides, goodbye. And I see chloride ion identical on both sides, goodbye. So our net ionic equation is this. What's left? So 2H pluses, 2 OH minuses, giving us 2 very badly drawn, there we go, water molecules. So that's the way our net ionic equation is going to look for an acid-base neutralization. And the hilarious thing, the last thing we should do, if all the coefficients are the same, and they are, we're just going to reduce all of them down to their simplest coefficients. So H plus, OH minus, H2O liquid. So I hope that helps you understand the concept of a net ionic equation. So you write the complete balanced chemical equation, you dissociate everything, you cancel out your spectator ions, and finally you write what's left. And you also reduce the coefficients if that is in fact, if they are reducible. Thanks, guys.